Okay, welcome to part 3 of our gravitation series. In this video, what I'm going to do is talk about the acceleration due to gravity. We're going to calculate g, and I'm going to derive out how to calculate it, and then most importantly, how to use it to calculate other g's on other planets, for example. So actually, what I'm going to do, although it's in words right here, I'm actually going to talk about it on Workspace. So let me do that. So you can use my slides to kind of revisit some of these ideas. So, when we calculate the force of gravity before we learned about the value, we always said mg. And we said that g on Earth is this value 9.81. Now, I did a lesson earlier in the lecture videos to show that this is true, even if you use the other form of gravity. But now we have another way to calculate gravity in our toolbox. G m1 m2 over r squared. So let me just draw a diagram of this. So, if this is the Earth right here, which is usually what we do, and this is the object, I'm going to call this mass 1, and then this object mass 2, and then the distance between the two will be our r. So when we're calculating force gravity in this sense, it's actually m2, because it's the mass of the person times g, like that. Well, notice force g and force g. These are the same force. If we have the same values, we can set them equal to each other. So what we can get here then is that force of gravity equals force of gravity, right? So force of gravity in this sense is m2g. That's from here. And then I'm going to plug in this one, which is g m1 m2 over r squared. So I hope you notice that when you have two variables on the same side of the equation, they cancel. And then we're left with g is equal to g m1 over r squared. And there you have it. So some of the important things that we're going to get from this is number one, g is dependent on the massive object, right? Or the central object. In this case, it was Earth, right? And when we said is Earth, but this refers to any object. So I can also do this with the moon, of course, right? So in this case, it would be of the moon. So I always say it's dependent on the massive object, on the mass of the massive object. Notice that it's independent of mass 2. So whatever's on the planet does not affect the gravitational acceleration, which hopefully should make sense. All objects accelerate. Another way to say it, all objects accelerate with g, regardless of mass. And here's mathematical proof showing that, right? So no m. So all objects have the same acceleration. G is also affected by height, right? So r. Well, I'm going to use the word radius, but it's also affected by height, right? So quite technically, if I put a person here on Earth on the surface, and we look at r from here to here, I'd say that I put a person on the biggest ridiculous mountain right here. That's a bigger r from here to here. Which means if we make r bigger, then this becomes larger, which means that number becomes smaller. So the further away you are from the surface, the lower the g. And that's quite technically true. The value is actually very low. It's not like a huge value, and I'll show you in the slides, but as you go up higher on a mountain, the value of G actually is not officially 9.81. It might be 9.80 or 9.79. It's small, but it is there. And vice versa. If we were to go closer to the Earth somehow, like go below sea level, then the acceleration that you feel is greater. So this is the big take-home, especially if you're doing AP. They won't usually have you calculate these values, but they'll have you change the mass and the radius to see how G is affected. So this is exactly what I derive here. The m's cancel, you get G. And exactly. So I do run through the calculation. You can just kind of see how I did it. I included the radius of the Earth plus Mount Everest, and actually at the top of Mount Everest, G is 9.75. So notice it's not super different, but it is, and that's the important part. So what we could do is we could calculate anything. So let's just for fun, go on the internet and find, let's do the, let's find the mass of Mars. So 6.41 to the 23. So I'm going to write that down. And then the radius of Mars. So we can find G on Mars. So let's go ahead and do that. So let's get a new page. So G of Mars, it's going to be capital M over R squared. So M of Mars, is going to be 6.41 times 10 to the 23 kilograms. I think that's what we had here. Might have to redo it. Here we go. 6.41 to the 23. And then, of course, the other feature we need is the radius. Radius of Mars. In meters, please. So 3.39 to the 6th. So go back to here. All right, so let's find G of Mars, and we can check our answer by looking it up. So this is how we know the gravitational acceleration on different planets. G is 6.67 times 10 to the negative 11 Newton meters squared over kilogram squared times the mass of Mars divided by the radius squared. So I'm just going to pause the video to calculate this.